can't be smaller than this bending angle because that's the angle that you're kind of smearing things out on. Okay. So let me just try to make this a little more concrete. So if you're looking at, let's say, a football field on the moon, and that was never built by the Apollo astronauts, despite it may read like the engine or something like that. They never actually built a football field on the moon. But a football field on the moon would have an angular size of about 1 second of arc, which is the same as a dime 3 miles away. So if you think of the size of a dime 3 miles away, and you think of looking at a football field on the moon, they actually have about the same angular size. But if your telescope doesn't have a resolution as fine as 1 arc second, then you're not going to be able to see that. You're going to see a smeared out blob on the moon. You're not going to see the millipose and the jumbotron and all those things you normally associate with football. So this bending angle, if it's larger than the angular size of what you're trying to look at, like jumbotron on the moon, you're not going to be able to read the score. And then, of course, that's, for Americans in particular, a very frustrating situation. Okay, so the actual angle of bending, this A thing I call here, it's in units arc seconds, double apostrophe. Remember, there's 3,600 arc seconds in a degree. So there's about 1,800 arc seconds across the full moon. Just to give you an idea, if you get the size of a full moon, you slice the full moon up, it'll be 1,800 arc seconds across. So that's how small an arc second actually is. Anyway, so that's the unit that they use here. And if we put in the observing wavelength that we're using, this lambda is the wavelength of the light we're using, which could be visible light. Actually, this formula works for any electromagnetic radiation, so we're even going to be able to apply this to radio waves and anything else. But we put that in units of angstroms, which are 10 to the minus 8 centimeters. And we put in the diameter of the mirror in meters, then this is the formula that gives us that little bending angle. All right, so first of all, remember that smaller here is better. Because the smaller that angle is, it means that your ability to see small details is better than it otherwise would be, right? Like if this bending angle turned out to somehow be something like 1,800 arc seconds, you wouldn't even be able to look at the moon and see the moon clearly. That would be comparable to the size of the full moon. But if this were as small as 1 second of arc, then you would basically see the moon with like 1,800 by 1,800 pixels across the moon. Lots and lots of pixels on the moon. Zoom in, see your jumbotron and all that. Nice stuff. So smaller is better. The smaller that bending angle is, the better the resolution is. So anyway, this is actually the theoretical limit of resolution for the telescope. So we say theoretical because in practice there's other effects. Okay? Particularly if we're talking about a telescope sitting on the Earth or the Earth's atmosphere. But in theory, if we had a telescope in vacuum, this would be the performance of the telescope. Angular resolution. Again, smaller is better. So when we talk about resolving power, better resolving power, we sometimes even say higher resolving power. You know, higher sounds like it would be a bigger number, but really, higher resolving power means a smaller value for that little egg. Oh, sorry, that's one of the things I should mention. So what you want to do to improve the resolution is you want to do one of two things, or both. You want to either increase the diameter, right, because the diameter is in the denominator. The diameter is in the denominator. So if we increase the diameter, the denominator gets bigger, the fraction gets smaller, A gets smaller, good, right? Or we can drop the wavelength. If we make the wavelength of observation smaller, you get better resolution. So we can do either one of those two things, or both, and we'll get better angular resolution. Okay, so this is what happens if we have poor angular resolution. If the spacing here between these stars is like 1 second apart, then clearly the resolution here is probably only maybe about 5 seconds. You know, it's such a big resolution angle, we can't see this 1 second of arc spacing. Down here, if this spacing is 1 second of arc, then the resolution is probably about a tenth of an arc second. So really clearly see what's going on. Okay, so we take the formula. We're not going to actually worry about where the formula comes from, but I'm just going to show you some examples of how this works. And then today we're going to move over and start talking about radio telescopes, and the same formula works for radio telescopes too, and we'll talk about that. All right, this is just about as far as we got last time. If we're looking at a 1 meter telescope, which is that's about 40 inches, that's a little bigger than Mason's telescope, which is about 32 inches, and it's on the research building. But if we take 1 meter telescope and we put that in the denominator here, we put in 4,000 angstrom to the light. We do the math here. So remember, we're using scientific notation here, so we have 4,000 and 4 times 10 to the 3, that land is 4 times 10 to the 3. And this fraction here, 4 times 10 to the 3. The diameter is 1 meter, so that's just a 1. Don't worry about that anymore. So the whole calculation comes down to taking 4 times 10 to the 3 and multiplying by 2.5 times 10 to the minus 5. So 4 times 10 to the 3, the 10 to the 3 can be combined with the 10 to the minus 5 to give you 10 to the minus 2. So we set that aside. 10 to the minus 2 is the exponent part. But we also had a 4 there. 4 times 2.5 is 10, right? So we end up with 10 times 10 to the minus 2, but that's actually 1/10, right? 10 times 100 is 1/10. So this is where this number comes from. 1/10 of an arc second. So that telescope, a 1 meter telescope, roughly the size of a Mason telescope, observing the blue light at that wavelength will have a theoretical limited resolution of about 0.1 seconds of arc. So not only could you see the diamond 3 miles away, you might even be able to read the date on the diamond or something like that. You're seeing details on the face of the diamond now with that kind of angular resolution. But as I mentioned here, that's actually less than what we're going to find is the atmospheric limit of resolution, which is 1 second of arc. So we're getting slightly ahead of ourselves, but the basic idea is that light has to pass through the atmosphere. And the atmosphere, to some extent, acts like a lens itself. But it's not a human-made lens. It's a blobby lens with different densities of air masses, as we work our way up through the atmosphere. And those different densities of air masses cause little bits of deflection of the rays of light coming in an unpredictable way, and that's what actually causes us to have this problem through the atmosphere, that we can't really view any astronomical object clearly that has an angular size less than 1 second arc because of the atmospheric problem. Anyway, but we'll talk about that in more detail in a moment. Now, let's talk about the Gale telescope, the single, fully functional, single mirror, the largest single mirror, fully functional telescope in the world. 5 meters, 200 inches, telescope, diameter. Again, blue light, theoretical limit of resolution 0.02 seconds of arc. Less than the atmospheric limit of 1 arc second. Now, we have a telescope here, sitting on a mountaintop in California. It can't achieve its theoretical limit of resolution because it's under the atmosphere. And in the atmosphere, even on the mountaintop in California, you're going to get that 1 arc second smearing out of the image. So, why? I mean, they knew about this when they built that telescope. So why in the world did they build this large telescope? If they can't achieve the actual theoretical limit sitting on the mountaintop in California. Any speculation about that? Anybody want to stand up and make a statement? One statement? Getting into the Bible, word for it? No? Probably not good. Want to see how big we can make a telescope so we can build something in the space like that? Well, I mean, bigger is always better in those cases, right? But there is a more fundamental reason, which is kind of moving in the same direction. The idea is that although this telescope is not going to achieve its theoretical limit of resolution, it's still a big telescope, so it's still going to collect a huge amount of light. So what that means is that you're not going to see the fine detail, but you're going to see a really bright image. I mean, the light isn't being absorbed by the atmosphere, it's just getting deflected a little bit, but you're still collecting all that light with this huge light bucket, 200 inches across. And so what that means is that although there is not going to be the achievement of the theoretical limit of resolution, if you look at a distant galaxy, Andromeda galaxy, a million light years away, with this telescope, it's going to be really, really bright. And you're going to see things that you can't see with a smaller telescope, like details about the distribution of stars and things like that. So bigger telescopes are still better, even if you're on the ground, because you're going to get a brighter image, even if you can't get a more detailed image. All right, the formula also applies to radio telescopes. Now here we're talking about observing with a wavelength of 1 centimeter. Now remember, an angstrom is 10 to the minus 8 centimeters, so 1 centimeter is actually 10 to the 8 angstrom. So that's what we would put in here for this wavelength. In this case, we put in 10 to the 8th power, because that's what 1 centimeter is an angstrom. The diameter, notice we're getting to ridiculously large diameter, 43 meters. That's because radio telescopes are really not, they're not made out of polished glass at all. They're antennas, basically. So they're made out of metal mesh, things that are easier to work with on large scale. So this particular telescope is one of the telescopes that's in Green Bank, West Virginia. Pop these numbers into the formula, we get 1 minute of arc. We actually have 60 arc seconds. 60 arc seconds is 1 minute of arc. So that particular radio telescope will observe with an angular resolution of about 1 minute of arc. By the way, remember the moon is a about 30 arc minutes across. This is still pretty good. If you're seeing 30, slices of the moon here with an angular resolution of 1 minute arc. Okay, now of course it's interesting to talk about what we can do in space. Because in space, the rules are completely different because we don't have the atmospheric problem anymore at all. So, you would naturally want to be able to observe with a telescope using the actual theoretical limit if you can pull it off, because then not only do you get that brightness of that big telescope, which actually can start seeing the fine details that we can't see from the Earth. So if we're talking about the Hubble Space Telescope, 2.4 meters across, around 3 times the size of the Mason telescope or so. If we observe with 5,000 angstroms green light, we would have a theoretical limit of resolution of 0.05 seconds of arc. So that's like a dime 6 miles away. And the thing is, although that's less than the atmospheric limit of 1 second of arc, it doesn't matter because this is kind of the elegant solution to the problem. You just put the telescope in space. You're above the atmosphere. The whole atmospheric bordering problem goes away completely. And the Hubble actually can observe, at its native theoretical resolution. It's the only large telescope in the world that can actually do that without using some sophisticated X-ray technology. So actually can achieve that resolution with the Hubble in space. Okay. You will see that, particularly when we're talking about radio telescopes, there are certain technologies that can be used to combine information from more than one telescope that can actually lead to a better angular resolution. But those aren't usable for output telescopes so far. Okay, so here we just have a situation where we're moving into better and better angular resolution and you see finer details. It's sort of like just having a single telescope and going out of focus with it. You have a telescope and you unfocus it, you're kind of simulating poorer angular resolution. And then, of course, this is the best we could do with that particular telescope. So you can clearly see that we're seeing finer details when we go to a smaller value for that angular resolution. All right, so large telescopes, clearly you're going to collect more light, you're going to have better angular resolution. So I just want to briefly talk about some guidelines if you're interested in buying a telescope for home use, obvious use. You can go into Walmart, Kmart, any of the marts, and you can get a telescope with a very high magnification. You can go into one of these places. You can actually see telescopes on the shelf that brag maybe 1,200 times the magnification in a small telescope. Well, the thing about that is, when people promise high magnification in a small telescope, it's sort of a scam in a way, because what they're really saying is that if you stick the eyepiece that they give you in the telescope that they give you, then technically you're enlarging the image 1,200 times, but you're not going to see anything because you're actually pushing the telescope beyond its theoretical limit if you do that. And if you just do that anyway, it's not like the telescope's going to blow up, but what actually happens is you zoom in so much on the image, you really don't see anything anymore. It just goes gray. It just goes completely gray. You're not seeing details anymore. The details kind of expand away and get fuzzy, and you just see a gray image. You over magnify beyond the limit. So what you really want to do is keep in a few hundred times magnification range for a typical small telescope up to about 8 inches in diameter or so. When you get larger than 8 inches to 12 inches or higher than that, that's kind of like a really serious, obvious telescope that most people don't buy. Then you can go to higher magnification. But in